Saxon's Calculus, Lesson 48, is about differentiation by U substitution. They launch into a box almost immediately in which they talk about the substitution axiom. If two expressions, A and B, are of equal value, in other words, A equals B, then A may replace B or B may replace A in another expression without changing the value of that expression. Also, A can replace B or B can replace A in any statement without changing the truth or falsity of the statement. Also, A may replace B or B may replace A in any equation or inequality without changing the solution set of the equation or inequality. So basically, substitution works without changing the problem, short version, and it works in a variety of methods. Now, I'm going to jump to example 1 to explain U substitution, but basically you're going to end up having to use this when your original equation isn't nice and simple like we've been doing, such as y equals x squared plus 2x to the 10th power, and it asks us to find the derivative of the f function. Now, this is messy, and so I do see that I have this something with the 10th power, and I know how to deal with that, but not this messy part. So this is where U substitution becomes helpful. I'm going to assume that U is the messy stuff in here, and then I'm going to derive that, and that's going to give me 2x plus 2. Now, back to the original, that means I have U, to the 10th power, because this was the U, and now it's U to the 10th power. When I derive that, I get 10 moving to the front, U to the 9th, du. So this is fixing the short little one, easy peasy, and here's the other parts that I used. So after you've done this U substitution, plug everything back in as you're finding it. So this is the 10. The U is x squared plus 2x. It's to the 9th power, and it's multiplying by du. So this is why it was very important that we learn to put that at the end of these when we were doing the differential. Okay, so now du is this statement. So it's multiplying with another 2x plus 2. One of the things that I say when they get even more complicated is make sure you are doing a derivative of every single piece of the problem. Now, this one with the U substitution will keep you straight, but when they get to be longer, you're basically doing this to the 10th, so you're deriving that part, and you're deriving the inner part, which we're setting as the U, and as long as we're doing derivatives of all the parts, we should be getting to the correct answer that we need to be at. Now, that was coming from a y, so dy over dx would be a good way to say I'm doing the derivative of that one. You could set it equal to the f prime of x there, and that would be okay as well. Now, example 2. If the h equation is h of x equals a cubed root of x squared plus 2x, find the derivative of the h. So again, we are going to set our u as the messy stuff, x squared plus 2x. We're going to immediately derive it to 2x plus 2. It just happens to be the same. And then in this original, this was u, 2, and the exponent for the whole overall unit is 1, and its denominator would be the third. Following the rule then, that would be 1/3 u minusing 1, that's minusing 3/3, so negative 2/3 du. Now we substitute everything back in, so 1/3 with x squared plus 2x to the negative 2/3 multiplying with the 2x plus 2. And then we could set the whole thing equal to, I'll do it this way. Okay, now this is not in its simplified form, so I can simplify this a whole lot more, although did they bother? 1/3, this one to the negative 2/3. Ooh, no, they did not. Okay, but if I were going to, because this is a negative exponent, I would be moving this x squared plus 2x down to the bottom, and it would be being squared, and then technically in a cubed root, and the 3 would be in front of it from the denominator here, and the 1 would be on top. But that 1 is going to get overridden by this 2x plus 2, which was multiplying by it. And then we could say that was our, so that's just another way to have written that answer. In example 3, if the G equation is natural log of x squared minus 42, find G prime of x. So we're going to set u equal to x squared minus 42, immediately do the derivative of that and get 2x, and the minus 42 drops off. And then this is natural log of u, and when you derive that, that's 1 over u, it's memorized, and then du. And now we will write 1 over x squared minus 42, plugged back in, multiplying with this 2x. I might as well just throw that up top because it was multiplying by the 1. And they have 2x over the x squared minus 42. They simplified it that way. There's our answer for example 3. Now, example 4. If the f equation is f of t equals sine of t cubed minus 15, find f prime of t. So we are going to set our u equal to t cubed minus 15, derive it, and get 3t squared. That drops off. And then that gave me sine of u, and the derivative of sine is cosine of u du. So plug it back in, cosine of t cubed minus 15, multiplying with, so I might put that in front to be honest, 3t squared, and then that would be our f prime of x. I don't think there's any other way to simplify that one. Just a second. Do I have a problem? Oh, no, I'm looking at the wrong example. I'm like, where did the t go? Yep, we are good. Example 5. They give us y equals sine cubed x. Find dy over dx. So we are going to u equals 3x. The derivative of that is 3. That's the sine of u. Sine goes to cosine of u du. So we have cosine of 3x multiplying with the du, which is 3x. So I'll just go ahead and put it in front. Just a second. I've done that horribly wrong because that doesn't say sine of 3x, that says sine cubed of x. Ignore that. Let's shift to a cleaner spot where I have room to work, and let's try that again. Y equals sine cubed of x. Haha. Find dy over dx. Okay, so our u is sine of x. Our du is sine goes to cosine. Then this was u cubed, which goes to 3u squared du. So 3 with our sine x, I guess it didn't need a parenthesis. 3 squared. Okay, so that would actually be here, or I could have put it on the outside since I'd used the parenthesis. So 3 the u squared du, multiplying that with cosine of x. So I think I will leave it as 3, and they put cosine first, but it doesn't really matter. 3 cosine and then sine squared with their x, and then that, of course, was their... Oh, they changed it back to this one, although originally they'd asked for dy over dx, so I would prefer to say that is dy over dx, but same thing. Now, example 6, we're getting closer. Y equals cosine times e to the x, find f prime. So our u is going to be e to the x. The derivative of that is still the same, e to the x. So our original makes that cosine, oh, that's lousily written, cosine of u. The derivative of that cosine goes to negative sine of u du. So negative sine of e to the x multiplying with du, which was e to the x. My guess is they're going to put that in the front. Yes, so they're going to write that as negative e to the x, and then sine of e to the x is, and I would have said f prime. And of course, they wrote it as that and the dy over dx. Okay, final example 7 on the top of page 245. If y equals e to the x plus 1 to the 1/2, find y prime. So our u is going to be e to the x plus 1. du will be e to the x. The 1 is dropping off. And then the original is u to the 1/2. So that's 1/2 u to the negative 1/2 du. Putting it all together, 1/2 u is e to the x plus 1 to the negative 1/2, multiplying with e to the x as the du. So then to rearrange it, I would put that e to the x in the top. I would put the 2 in the bottom. I would move this down to the bottom to make it positive. And I could choose to put that back into a square root because that's what that 1/2 means, but I'm going to leave it with that fraction. They left it with the fraction, and then it equals your y prime.